Welcome back. Second lecture of week 12. As I had told you in the beginning of this week, we're going to look at a small variety of miscellaneous topics. The first lecture we saw regression testing. This one is on software quality. We'll understand what software quality is. Testing is all about assuring software quality. Some metrics for software quality that you must know having done a course on software testing. That's this lecture. In the next one, we will look at some of the ways of testing for quality, which constitutes non-functional testing. So, overview of this lecture, we'll understand what is software quality, small variants of the term related to quality, some general software metrics, which you should have seen in your software engineering course also. But I will give an overview of a very small subset of software metrics and maybe a list of software metrics for object-oriented software because they can be measured with a lot more quantified details than normal software. And then we will look at metrics specific to software quality in detail because that's what you need to know as a part of the testing course. So what is software quality? The English word quality says that something has to be up to somebody's expectation. The food is of good quality. The singing was of good quality. The camera was of very good quality, so the movie was good. The sound quality was good. So we use the term quality to say something that meets our expectations. Same thing holds for software also. Software should be of good quality means software has the ability to conform to its required set of specifications as given by the customer or stakeholders. And there are several different standards of the software. If you remember, in the first week, I had told you about ISO standards. There are similarly IEC standards. Each of these standards have their own definition, but what I have given you here is a definition as per one of the standards, ISO standards. So software quality is the capability of a piece of software as a product to conform to its stated requirements. Obviously, if a software is of poor quality, it can be error prone, it can be slow, and the cost of such software can be expensive in the sense that if there are errors and if it leads to failures and faults that cost life or loss of finance, then it can be expensive. Fixing that can be expensive because it can cost further development. So in general, if quality is poor, then it means higher costs. And so we don't want compromise on quality. Many companies strive to live up to the quality. There are standards like Six Sigma and CMMI that talk a lot about software quality. So in software engineering, quality can be of two kinds. One is related to the functionality of the software. We call it software functional quality. It's a measure of how well a piece of software complies with or conforms to its given functional requirements or specifications. Let's say a software is supposed to calculate somebody's income tax given all the constraints correctly, then functionality says it will do so. Right? Software is supposed to tell you some functionality related to using your bank account. It will tell you correctly so. So that is related to functional quality. It talks about how well a software conforms or complies to its requirements, design, and so on. So it is the extent to which correct software was produced, and testing, which is what this course is all about, is the most predominantly used technique to ensure functional quality of software. The next is related to the structural properties of software. We call that structural quality. This talks about how robust a software is, how easy it is to maintain a software, how pleasing is it in terms of its user interface, how fast it is in terms of its response, how portable it is in terms of working with different operating systems or web browsers. So these deal with not the core functionality of a software, but more of its non-functional requirements. Like for example, suppose a software is supposed to provide banking interface that lets you log into your online banking system, check your balance, maybe transfer through NEFT, and do a few other functionalities. The software should be portable. It should be available from different web browsers or maybe even from a phone. The software should be usable in the sense that its language should be good, user interface should be good, and the software should be secure. It should not let unauthorized users access somebody else's bank account details. The software should perform well. It should be fast enough. So these are related to non-functional requirements, otherwise known as structural quality. If we drop the term functional or structural and just refer to quality, we are mostly talking about non-functional requirements. So it is the degree to which a software works as it is expected to work, not in terms of functionality, but in terms of other structural aspects of its quality. So in software quality, we talk about two things: software quality assurance and software quality control. The only two terms that differ in these phrases are that of assurance and that of control. So what does assurance mean? Assurance is some kind of a guarantee that you provide. So you pursue a set of activities or tasks and ensure that a software, the quality requirements specified in the software, ultimately actually supply that kind of quality, assure that kind of quality. So these activities establish and evaluate the processes that produce these software products. It focuses on a set of practices or processes that you follow as a part of an organization to ensure that the software meets its quality requirements. That's assurance. Control is basically a set of activities that ensure the quality of the software products, not really process quality, but more of the product. So this is directly testing, right? Testing is an activity that involves software quality control. It actually focuses on finding errors, fixing them, eliminating them, retest to ensure that the errors don't come. So this involves a product focused, and testing is actively a software quality control measure. So now let's look at metrics. Typically in sciences and in engineering, we always want to measure things, to quantify things. So the same thing happens in computer science and software development. Software metrics act as a good source of quantity or data that can be measured that indicates various parameters or features of the software. We'll look at generally a few software metrics, then we'll move on to software quality metrics, which are specifically used in the context of testing. So what is a software metric? It's basically a measure of the degree or the extent to which a software system or a process used to develop a software possesses a certain desired property. For example, you could say the software has to be packaged into a mobile phone that is of not very high memory. So you could say one metric is the packaged software should be of a few MB size or a few KB size, because it should be downloadable in a phone as an application. Then you could say a software should be available as a replica of itself because it's safety critical. So that could be another kind of metric or a measure that talks about another property of software, and so on. So software metrics, like we say in science and engineering, are useful in providing quantifiable measurements, things that I can use for measuring and say that such a number means good quality, such a number means bad quality, and so on, to various software development processes, the steps that are followed to develop software, and the software itself, right? So if I have a set of metrics, I can use them as the basis to measure and talk about certain properties of the software and certain properties of the software development processes. So there are various kinds of software metrics that are available. A set of metrics that focus on the final product, that is the software itself. A set of metrics that focus on the procedures, the development life cycle processes, those are the process metrics. And a set of metrics that focus on the project aspects of it. So first one is product metrics. It describes the various characteristics of software as the final product. Size, which could be the number of lines of code. Complexity, which could be cyclomatic complexity, coupling, cohesion, and a few things like that. Metrics related to its design, how simple or complex the design is in terms of polymorphic methods, inheritance of classes, use of control logic, and so on. So they directly talk about the product. For us, it's the software. The next is about the process. That is, what are the steps that I follow to ensure that a software is of high quality? I do requirements baselining. I do traceability of requirements. I do high-level design followed by low-level design, and maybe eliminate defects there. Have processes to find and eliminate defects there. Then I do coding followed by unit testing. Then there is a quality auditor who reviews this. So these are process metrics that talk about what are the characteristics and how to measure them in terms of producing a high quality software. The third one is project metrics, which describe the characteristics of the project and its execution. Project is obviously developed by software development teams, and so we are going to talk about the team size and the kind of people that are there in the team, expertise that is available in the team, systems engineers who are architects, designers, coders, developers, team leads, project managers, test engineers, and the cost of the final development of the entire software, the schedule, how many months, man months, what is going to be the productivity. So those are project metrics. If I take a particular metric, a specific metric, it can belong to more than one category. These are not mutually exclusive. Some common software metrics, I'm just listing them, not really defining them because you should have seen them in the software engineering course. Most common software metrics is how long the software is in terms of lines of code. Uncommented lines of code. Ignore the comments or the documentation and then count the lines of code. Usually non-trivial code is more than a few thousand lines of code. So we always count lines of code in thousands. That K here in KLOC stands for 1000. So you say number of 1000 lines of code. So if you say 5 KLOC, 5000 lines of code, things like that. The next is cyclomatic complexity. We already saw this when we looked at testing for source code. The next is program size. If a program is packaged and made available to run as a part of a RAM or stored in a hard disk, how much of memory does it occupy, right? So that's the size in binary. Then there are two important metrics which you should also know. One is that of coupling and the other one is that of cohesion. They are complementary to each other. So let's see what they are. Coupling is the degree of interdependence between software modules. It is a measure of how closely the two connected modules are. Like for example, you say we saw coupling data flow, right? So you say some variable is coupled with some variable on a call interface. So we say two modules are connected by that call interface with a set of coupling variables. So that is also a metric. So it's the degree to which you can talk about how two software modules are dependent on each other. A related one is that of cohesion. It's a measure of strength of the relationship between the methods and the data in a particular class. All the methods that belong to the class, are they cohesive? Put together, do they offer one functionality? Let's say if I have a class that implements a stack data structure, then I need methods for push, pop, checking if a stack is empty, and so on. So these methods must belong together into one class and provide similar identical functionality that helps us to identify or relate to the class. That is the notion of cohesion. Coupling and cohesion are complementary. High coupling could mean low cohesion and vice versa. We're not going into the details. I'm just giving you an overview of the list of common software metrics. Now, if you have object-oriented software, your design is rich in object-oriented, as we saw in the past couple of weeks, then you can define a whole set of additional metrics specific to object-oriented design. I've just listed them. In the last slide, there is a reference that defines each of these. As I told you, the goal is not to look at software metrics as a part of this course, but more to look at software quality metrics. So I've not given the definitions of these. For example, you could talk about number of children here. If you see the last but one, it talks about the class inheritance hierarchy, the descendants of a particular class, the parent class, the ancestor classes, Do I have a multiple class inheritance hierarchy, or is it single class inheritance hierarchy? That is a quantifiable metric. Weighted methods per class, a member of methods owned by a class that can be assigned a certain weight based on certain features is another metric. Then inheritance of a method is related to polymorphism. That could be another metric. Several different extra software metrics can be defined if I have object-oriented software. Let's now move on and look at metrics for software quality because they directly relate to testing. Some common software metrics are what we are going to see. Basically, software quality metrics are a subset of software metrics that focus on the quality aspects of software. They are not associated with project metrics. You see here, we saw product, process, and project, right? Quality metrics usually talk about the product metrics and the process metrics. Very rarely do they talk about the project in terms of the human resources and things like that. So there are three kinds of software quality metrics. One that focuses on quality of the product, one that focuses on quality of the process that involves in developing the product, and another one that focuses on maintenance quality of the software product. So we'll see what they are. Product quality metrics. Here is a small list of them. The first one is what we call mean time to failure. Software fails. It can fail for several different reasons. And between failure 1 and failure 2 and subsequent failures, you measure the time and take the mean value. And this is considered an important metric. If a software fails often, then it's really error prone, very low quality. But if it fails, almost never fails or fails very rarely, then it's of very high quality. So it's mainly used in the context of safety critical software, which is expected to have very negligible, very high mean time to failure. The next is defect density. It talks about given a unit of code in terms of number of lines, let's say given 1,000 lines of code, how many defects are found on an average for every 1,000 lines of code or for every certain number of lines of code, or how many defects can be found for every certain number of function points in the code. So defect density measures the number of defects relative to a size of software, which could be in terms of lines of code or function points. The next product quality metrics could be basically just the number of defects or issues reported by customers per unit of time. How many issues came every month, every week, every quarter, and so on. So that's a simple metric to evaluate the quality of software as a product. Then satisfaction of customers. Usually you take feedback on a 5-point scale. Very satisfied, satisfied, neutral, dissatisfied, very dissatisfied. Some 5-point, 7-point, 3-point scale. And that is a simple way, a user study to measure how satisfied the customers are with reference to a certain kind of software. Then we'll move on and look at in-process quality metrics that deal with process aspects of software. This basically, you have formal testing. There is this term called machine testing that people do, but think of it just as testing. So this is basically a whole set of metrics that tracks the arrival of defects during testing. One is defect density, same as what we saw here, measures the number of defects relative to a unit of code. The next is defect arrival pattern. Here we saw this, issues reported by customers is the number of defects that they report, but you could say the same thing, the number of defects found per unit of time. It could be as granular as per week, per month, per quarter, and the collected defects which weren't fixed, defects found but not fixed. So they also add to the arrival pattern. If the arrival pattern gets denser, then the software is deteriorating in its quality. Then phase-based defect removal pattern. Sometimes, how many defects were found in a week and what percentage of that were removed in that week or subsequent weeks. How many defects were found in a month and what percentage of that was rectified in that month and subsequent month. Phase basis, we talk about what was the pattern of removal of defects and how effective removal of defects was. in terms of quick, time consuming, not time consuming, and so on. So defect removal effectiveness, if you want to look at it in detail, abbreviated as DRE, is this ratio. Defects removed during a development phase by defects latent in the product into 100%. So this is useful for tracking the defects in each phase of software development. As and when I find at the design phase, at the requirements phase, at the coding and unit testing phase, if I've removed them, that's fine. If they trickle down to later phases in the software development, then they're going to get expensive when they're found. They're going to get expensive to fix. So early removal is recommended because it indicates a lot of saving in development cost and time. Now let's look at quality metrics that are involved while maintaining software. So we saw product quality here. Then these are process quality metrics. Now we're looking at maintenance quality metrics. So here also the software is released, it's being maintained. We saw what it means to maintain a software when we did regression testing. What kind of metrics matter in that case? These are some metrics. One is related to backlogs, how many backlogs have been fixed or managed. One is related to the time that it takes to fix an error that was found. One is called percent delinquent fixes. I'll tell you what it is. The other is the quality of fixes. Quality of fixes, we're not defining it properly here because it just each company or organization will have their own measure of what is quality. But let's look at fixed backlog and backlog management first. Fixed backlog and backlog management is measured using a term called Backlog Management Index, BMI. We do have BMIs in testing and quality also. BMI is defined as the number of problems that were closed during the month, a ratio of the number of problems that were closed during the month to the number of problems that were found or that came up during that month. So a simple count here of the problems that have not yet been fixed during a certain time unit helps to tell you how much of backlog you have as far as your fixes are concerned and whether you've been able to manage your backlogs well. So that is Backlog Management Index. So the rest are related to this. I'm not defining them formally, but they come up when you're doing maintenance of software. So this was a small cursory introduction to software quality, software metrics, and software quality metrics. If you'd like to know more about it, this textbook has some useful reference. Some of the material that I taught here are taken from this book. And specifically to object-oriented software metrics, this is a very good reference. I will make the PDF available to all of you along with the slides. I'll stop here. Thank you.